All right. Well, thank you all for indulging me there. I thank you all for giving me the opportunity to actually speak with you today about some work that I've done with my co-author, Chris Gardner, on trying to understand what features are being learned by these byte-based malware classifiers that Octavian just so eloquently talked to you about. So as I'm sure many of the people in this room understand, feature engineering is kind of the bane of our existence as far as ML goes. It's a really hard task, and it's especially so for something like malware classification where you need just a ton of expert knowledge to be deriving those features. I think it's pretty natural for us to look at something like deep learning and to see all its successes and ask the question, well, if it can do it for images, why not for malware? And in fact, that's what's been happening, right? So the last 2 or 3 years, there's been a number of papers out there that have looked at applying convolutional neural networks to automatically learn feature representations directly from the binary data of Windows PE files. And honestly, they've shown pretty promising results here. They're competitive with, though for sure not as good as, traditional machine learning models. And so what I want to start with is just to kind of give you FireEye's perspective on this. So over the last 2 years, FireEye has been working on our own CNN model. We're actually one of these papers at the top here. And so I won't go into the gory details of the model itself, and this is obviously a very simplified picture of the model. But I will point out a couple of things that I think are unique or different about this model. So one is we're quite deep, right? Especially compared to something like malconf. We have 5 convolutional and pooling layers. We also use hierarchical pooling. So at each layer, we kind of group together nearby bytes to encourage locality-related features. And we'll see why that actually plays a role in the features that are learned here in a bit. So we're going to actually look at 3 different instantiations of this model, what we refer to as the baseline, which has about 15 million training samples with a 80% goodware to 20% malware ratio, collected over about 2 years. We have a small model, which is about half the size of training volume, split into a 50-50% goodware malware ratio. And then we look at a dropout model. And really the dropout model here is the same as the baseline model, but it adds regularization in the form of dropout before each of the convolutional network layers. So just as a single data point on these three models here, we collected a data set of 16 million binaries from VirusTotal and from Reversing Labs feeds. And we did that from June till August 2018. And now you'll see all the way on the sort of right-hand side the test results. Now, what probably is jumping out to you immediately is, why in the heck is the small model doing better than all of these other models, despite having half the data and having older data too, right? It was from 2016 versus 2017 in the baseline model. And so this has kind of led us to these big questions that we'll try to answer a little bit in this talk and more so in the paper. So the big question, right, is what exactly are these learning in terms of features? And then second, what is the impact of data volume and regularization in these models in terms of what those features are that are being learned? And ultimately, its impact on the performance of those models. So we do this via a 3-step analysis process. So we start from the lowest layer of our model, the embedding layer, and we look at clusters. We basically apply an HDB scan clustering algorithm to identify clusters and outliers, and we visualize those using multidimensional scaling. Moving up just one layer to the first convolutional network, or the first convolutional layer, we're going to go ahead and look at all of the high-weight activation areas for the binaries and disassemble them to try to get back to some sort of notion of human interpretable notion of where those activations are happening. And then finally, we're going to do an end-to-end analysis using the Shapley, or so the SHAP framework, to try to understand for each of those byte segments what their relation is to either the benign or malicious conviction of the model. So just to jump right into some of these examples that we have here, and there's quite a lot here, so I hope you'll forgive me if I kind of gloss over some of the details. So what you see here is your 2-dimensional, multi-dimension scaling visualization of the 10-dimensional embedding space. The clustering was performed in the 10-dimensional space. And basically what you see here is these dark points are all the points that were actually assigned to clusters. and the colored points are outliers. So you might be asking yourself, well, why are we looking at outliers and not the clusters themselves? Well, I'm going to give you a little bit of intuition, at least my personal intuition here, which is that outliers are more interesting. Clusters of tightly grouped bytes in this embedding space can naturally be replaced for one another at relatively low cost, whereas outliers are somehow being treated as unique or sort of special, distinguished by this model. And so we actually learn a lot about what sort of the key components, or in this case, given how low we are, the sort of anchor points you might think of the higher level features will end up being by looking at these outliers. So here's the outliers for the baseline model. Again, there's a lot of interesting stuff in here. I'll just highlight two of the more interesting bits. So there's a large number of ASCII character related bytes in here. And there's also a number of instruction level features or bytes, which are things like the registers, padding bytes. On the other side that I don't have highlighted there is a typical anti-debugging breakpoint instruction. So lots of interesting stuff that's kind of popped out here. And we'll see in the next level up how these actually get used to kind of coalesce into features. To add a little context, though, let's look at these side by side with the other two models that we have. So I would ask you to kind of look and read left to right here as you're making these comparisons. So in the small model, you have relatively few outliers being identified, a large number of clustered bytes. And as we move over to the dropout model, we actually get to the point where we have so many outliers, about 150 or more, that in fact the dropout model, you can't even like show it underneath the dropout model reasonably. So, you know, again, my interpretation of this, and there could potentially be many, so I'll put that caveat out there. But my interpretation of this, right, is that the small model is somehow learning more flexible features, right? There's less sort of key bytes that need to be present, and there's more opportunity for mutation within each of those features. And again, I'll show this, an example of this in the next layer. As we move to dropout, though, we get to very, very specific bytes. We get, you know, basically almost every single byte that we see absolutely has to be there. And when we think about how this is going to apply in the next layer up, this is clearly going to have an effect on how strict those first layer feature detectors are going to be. All right, so now we bumped up one level, right? Now we're looking at the first convolutional layer. This convolutional layer has 96 filters in it. And so what we did is we went ahead and looked at, for each of the files in our data set, the top 100 activations, and that is weighted by their weight across all of these filters. And we see a couple of interesting high-level things pop out immediately, right? First of all, despite the fact that this model has 16 million samples trained on it, you'd imagine it would try to use the full capacity of this layer. In fact, what we see is that there's actually a number of these filters that are just never used at all, right? So in some ways, it's not even using the full capacity yet of your first layer. Another interesting thing is that actually almost all of the filters themselves are used in both the malware and the goodware examples. So there's no obvious filter that is just goodware or just malware. However, when we go and look at actually the percentages of these activations for each filter, and you might sort of capture it, I tried to put it on the same scale here, there's a lot more malware activations in most of these filters than there are goodware activations. So you immediately get this sense that what's really being learned here are not necessarily generic features of the binary, but instead some sort of notion of, and I'll get back to this maybe a little bit later, the notion of actually sort of flexible antivirus signatures. Again, let's put the context up there to sort of see how things change over time with different amounts of regularization and volume. We see on the small side of the small model, very few filters are being used. And this is kind of to be expected. It's a smaller data set that doesn't need to use as much capacity. At the same time, if we are right about those flexible features being used here, then in fact, you don't actually need to use that many filters, right? Because the same filter can actually match a number of different sequences of bytes that underlie the actual, that are in the actual binary. Now, as we go, of course, all the way to the dropout model, we go from very few bytes to basically very few filters being used to pretty much all of the filters being used, which again is something we would sort of expect. When you add regularization, you would expect it to be using up all the capacity of that layer at this point. Now, the thing that's interesting about this is that whereas the baseline and small model had this huge predilection for having activations towards malware, that is, you kind of imagine that the features are more malware oriented or focused, this dropout model actually was learning features that were basically evenly split, 55% and 45% activations on the two data set, the two splits of the data set, the two classes. So it's kind of an interesting concept here that dropout model was doing much worse, and it has somehow learned what I would consider to be a more classically defined generalization of this the underlying feature space of the model, and yet it's doing much worse. Whereas these other things have, in some ways, somewhat kind of overfit notions of features, and they're doing much, much better on these held out data sets. So to give you just a taste of what some of these features actually look like, I've pulled out a couple of anecdotal sort of filters and their representatives here. And I'm just going to focus on the strings just for the sake of time. So the first thing you notice here, right, in all the strings features is they're basically all capturing imports, right? It's cryptography imports, get proc address, directory-related imports. The thing that's interesting, though, is if you look at the full breadth and depth of things that are being caught by each of these filters, it really does sort of cement that notion earlier that this small model, for instance, actually has filters that are quite flexible, right? Yes, it does capture crypt, related APIs, but it also captures a whole variety of other things, some of which are complete garbage and some of which are actually interesting other imports. But then by the time you get to the dropout model, you literally have a filter that is looking for nothing but the word directory, right? So that kind of, I think, underscores this weird notion that it gets more and more specific, but actually that specificity has hurt this model in some way in terms of performance. So now this is the last part here. We're going to look at the end-to-end features. So to interpret this illustration here, on the x-axis, you're going to see basically the byte offset into the binary that we're looking at. And then on the y-axis, it's the SHAP value associated with that specific byte segment, with obviously more positive SHAP values being sort of more in tune with a malicious classification. And again, there's a lot to unpack here, but the thing that I thought was kind of interesting was how closely related some of these features are to things that I have seen and I've used in traditional ML classifiers. Things like, is the checksum valid? Is the import and export table in a weird position relative to other structures in the PE file? Going on to kind of bring in the other models, you actually see similar sort of things going on, right? You see some import related things in the dropout model. You see the requirement of sort of this time date stamp formatting, which also is something that's a pretty standard manual, sort of manually derived feature. But kind of the overall trend here, again, is that in the small model, it's actually accumulating evidence over a large number of these PE file structures in order to make its conclusion one way or the other. Whereas, again, in the dropout model, and again, probably due to the specificity of the features it's learning, it actually is basically relying on only three features or three structures in that PE file to make its conclusion. So in some ways, it's almost a little bit more brittle in terms of the classification space. The last thing I wanted to mention here as I wrap up is just the appearance that the model can actually detect whether or not certain structural features are present or absent, which to me was sort of counterintuitive, right? It doesn't have any knowledge of structure. How does it know that, for instance, this rich header is something important to have? So I want to dive in quickly to the case of that rich header, right? So the rich header is basically just something that Microsoft Linker throws in. It's got some metadata about the compilation process. The interesting part now from our feature analysis perspective is that it is in fact actually sort of XOR encrypted with this checksum value. So it should effectively be randomized. There should be nothing in that space that is obvious to the CNN as to what the feature should be. It should be random from one file to the next. The hypothesis that we have here as to why some of these bytes are actually being triggered on is not necessarily the bytes inside of the rich header itself, not the randomized bytes, but it's actually these the presence of these fixed bytes, right? So for instance, for the rich header, you have this literal RICH, rich, string that's placed in there. And these are actually strings that tend to happen throughout the entire structure of the Windows PE file. So what I think is interesting that's happening here, or at least I think it's happening, is you basically have a hierarchical pooling mechanism that is able to maintain locality. The locality can then understand that, hey, this string that I would normally expect here is here or not here, and can understand like how much spacing in some ways there is between each of those different features as it goes up the hierarchy. So it kind of underscores the importance of that hierarchical pooling mechanism. Now, how does that pertain to malware? Well, in a traditional classifier, we actually have a feature that basically looks at the compiler and says, was this a Microsoft compiler or a Delphi compiler or some other crazy compiler? And actually, it sounds like a completely spurious conclusion here, but a really non-trivial amount of malware uses non-Microsoft toolkits to do this type of compilation. So in fact, it is kind of reverse engineered and learned this manual feature that otherwise it's unclear how it would have learned it on its own. So to wrap up, you know, I think that we've seen here that CNNs can create some really interesting and learn some meaningful features. You know, in my mind, a lot of these actually mimic manually derived features that we use, imports, checksums, the presence and absence of certain headers. I'm not going to go into any detail about it, but there was a recent paper by Demetrio et al. Who kind of come to a slightly different conclusion, though honestly they're in a slightly different space and looking at a different model. So it's not exactly apples to apples, but I think it also kind of highlights the difference when you're looking at different models and different data set sizes. Yeah, and honestly, I think that if I were to kind of pull out sort of the why here, it's really model depth, data set size, and this hierarchical pooling notion that appear to be key to allowing us to do these, learn these meaningful features. The last bit here is really just sort of a summary of everything we've seen comparing these small baseline and dropout models. And that's simply that it really appears that actually learning malware indicators is more important to malware classification than modeling overall the idea of a Windows PE file in some well-defined way. So I'll leave it here. I'll say that FireEye data science team, which I manage, is hiring. So if you're interested, if you have students that are interested in talking to me, please send them my way. My contact information is there. And I'll open it up to any questions you guys have.
Okay, do we have questions? I can certainly start off. So one question that I had is that it seems like all of the features that it's learning are sort of things about the metadata of the binaries. Yep. And I was curious, you know, you had a couple examples of like assembly snippets that it had picked up on, but how important were these kind of code level features to the models?
Yeah, that's a great question, and something we kind of explore a little bit in the paper. But the gist is, or at least what we've seen, is that these code level features do appear in like the first levels of feature detectors, the low level feature detectors. And in fact, some of the snippets that it learned were actually pretty interesting. They were like named exploits that it was picking up on. So clearly there's something interesting learned there. However, it kind of disappeared once we got to the end-to-end feature analysis. Those code-oriented features sort of just went away. Now, the follow-up to that is to say, from a traditional machine learning perspective, relatively few, not none, but relatively few of the features that we would use in manual feature engineering there have to do with like very specific code snippets, just because of how much those change, right? So that's my only kind of sort of aside there about the code snippet stuff.
So thanks for the talk. So this was really counterintuitive that training on a small data set helps. And I've been thinking the whole talk about it, actually. And I was wondering, can you say something about the temporal size of the data set? So I saw in your paper that you used a temporal split. So yes. Perfect. So this could not be the reason. But maybe this is a very short period of time, like a day or so, because I mean, so this would basically also contradict with learning theory, which says that if you have an infinite amount of training data, things get better and better until perfection.
Yeah. No, I 100%. I mean, that's why I actually set up with this this result, because this is kind of what drove me down this path. It was like I don't understand what is happening here to make this result. So, you can kind of see like the small model is. Oh no, they took it away from me. As I'm like clicking here, yeah. So basically, the small model is trained between July 2016 and November 2016. The test set is between June 2018 and August 2018. And the other ones basically are just a slight expansion of that time frame to like 2015 and 2017 around it. So yeah, I wish, so I think this kind of goes back to my underlying hypothesis that I'm getting to after this, which is I believe essentially that these CNNs are learning complicated and certainly context aware, but essentially they are learning to become AV signature engines. And the more broad your signature engine is, the better. But also, the more flexible your signatures are, the better, right? If you have very particular signatures that only match on very particular types of files, and you use all that capacity at that first convolutional layer, you may actually, in fact, be hurting your generalization with respect to this sort of AV classification, or sorry, AV signature problem.
So I have a short follow-up question, just because so have you thought about using something like bagging, where you train multiple models on small data sets? Because this would be my next step.
So we haven't gotten to there yet. So actually, I think one of the questions that folks asked for Octavian was like, so what's next here? And I agree with 100% with what he said, right? The byte-based approach has obvious, like we don't want to just get to another signature-based AV, even if it's easier to run signature-based AV. So I think one of the things that we're doing next is kind of trying to imbue some of the sort of syntax and semantics and structure into the architecture itself, right? So one of the examples is that just recently I finished running something that actually tries to break up into different sections, like executable section, resource section, headers, and actually learn specialized features for each of those, right? So basically they all have their own separate convolutional layers that can learn their own specialized features, instead of trying to basically jam, all this context and all this syntax into like just 96 filters at your first layer, for instance.
Okay, do we have any other questions? Oh, okay, got a couple over here.
Hi, I'm Javier Echauz, Symantec.
Hi.
Very nice talk. I guess your coworker Christopher is a reverse engineer,
Yes,
as we do have as well.
Yep.
And do you have any idea if this person can actually visually agree with the features that the deep network that you're developing?
So that's actually how we did this.
Is that it?
That's actually why he's on the paper. He did a lot of the grunt work of like,
Okay.
hey, I found activations at this byte offsite to this byte offset, and he would actually go in, bring it into IDA, like look and see what's actually happening there, and kind of validate what I was seeing. Yep.
I think it's very interesting that you brought up the. I'm Cristian Craveanu from Microsoft. I work in anti-malware space as well. I think it's very interesting that you brought up the reverse engineer in the question. You mentioned at the beginning that feature extraction is hard, but then you have an entire team of highly skilled reverse engineers that know what is important from the point of view of malware. It's a very hard problem if you think about and compare with image analysis, for example. In image analysis, you want to extract a certain feature, which is, when you compare with all the images out there, the feature is a small percentage of all the images out there.
Yep.
But you are looking for two things, malicious or good, where most of the things are good. So as your set expands, it's more or less random. Because if the bytes 0 to 255, the more bytes you bring in the picture, the more randomness comes in, and you're losing all the context.
Yep.
I believe feature extraction may be more useful, and bringing in the skills from researchers in the
so
picture.
my only sort of retort to that is just so I think feature engineering and manual feature engineering and extraction works really well when you're working on just a single file type. If you're just working, you only care about PE files, yes, you can absolutely do that. We've done that. It was a nightmare. because then you have to worry about having a robust parser for that file type. You have to make sure that the features are actually extractable using that parser, and then you have to make sure that the features are keeping up with reality, right? Now, I want to go and take my Windows PE, next gen thing and work on Mach O or, ELF or something. That's a whole new process all over again of 6 months of work to build that. Now, compare that to this, where literally I took this same exact model, no changes, applied it to Mach O data, and it worked with actually better accuracy than this one did. So, there's a lot of benefits here. Now, the question is, where's the trade-off point, and at what point do you need to imbue so much information into this to make it really strong that it's effectively the same as doing the feature extraction manually?
With regards to accuracy, 0.98% accuracy is really not acceptable for a security product.
Yep, agreed. This is not our production model.
Okay.
Our production model is using traditional ML, and it's it's like 5 nines accurate. So, but that's why I said at the beginning, right? It's not there yet. It's not better than traditional, but it's competitive, and it actually, again, if it plays out, if it is helpful, I feel like it could be a huge boon for the industry.
Okay, so we've got one last question, then we should move on.
I'm Scott Heidbrink from Sandia Labs. I was wondering if you guys had looked into different architectures, like instead of CNNs looking in sequence or attention layer networks, or even perhaps training embeddings separately to force kind of this instruction understanding before you feed it into a malware detection classifier.
All of those things. No, I mean, for serious though, we did actually explore, in this particular project, we've explored RNNs, other types of attention mechanisms. We've looked at the byte embeddings, but not necessarily in this particular case. It's actually more for like code similarity type of things, using the embeddings in that way. Yeah, I mean, I think this is why it's kind of exciting to me. There's a huge space of opportunity. This literally, to me, is like the absolute straw man model that we're working on here, and it's already doing okay. And like, yeah, it's not great, but I think there's a lot of opportunity to grow here. And I think not just that, but I think it's also a lot of opportunity to understand like the problem space, right? Like, if you had asked me before I did this if malware classification was going to be equally important about learning goodware and malware features, I would have said, yeah, I mean, building up a more robust understanding of Windows PE files is probably a good thing. After watching this and after going through this whole research, now I'm like more set than ever that basically what we need is a whole bunch of really important malware indicators, right? So I think there's a lot to be learned here, in addition to just trying to find the one model that'll do well enough, and then we can punt on it.
Okay, so let's thank the speaker again.